Thank you, everyone, for coming this afternoon. Our next speaker is Padmaja Bhagwat. And I'm trying to get her name right. I'm sorry if I just butchered that. Please give Padmaja a warm PyCon welcome as she talks about algorithmic music generation.
Hello, everyone. Thanks for being here. This being the last talk of the day, I want to make it as interesting and interactive as possible. So before starting my talk on algorithmic music generation, I'm a little curious to know how many of you present over here love listening to music. Oh my God, OK. I hope you enjoy this talk, because I'll be playing little music here and there throughout my entire presentation. To talk about myself, I'm Padmaja Bhagwat, a junior pursuing my bachelor's in India. And art, music, dance are something that I'm really crazy about, and coding is something that I love doing. So when you try combining these two fields, when you try combining both art and technology, you end up getting something really beautiful. Today, I'm here to present one such exquisite piece of outcome that we got when we tried combining both music and technology. So these days, we have seen computers doing incredibly amazing things, such as speech recognition, character recognition, time series analysis, image classification, and the list just goes on. But what about its usage in art? How far have we come across in terms of using artificial intelligence in the field of art? So in this entire presentation, I won't be talking about the ability of computers to identify certain objects or to classify certain things, but I'll be focusing on the ability of computers to generate something as good as music, and how Python made all these seemingly complicated tasks much, much simple. So as I had promised before, I'll be playing two sample music. Please listen to it carefully. Here's my first music sample. There was my second sample. OK, now can you tell me which one of this is real and which one is artificially generated music? OK, I can see there's some sort of confusion. So there's a saying in Hindi, it says, sabar ka phal meeta hota hai, which means it's good to wait some time, because I'll be revealing answer to this question by the end of this talk. Till then, I hope you can wait. So let's get into the technical part of this talk. So this entire process of algorithmic music generation is broadly classified into three main steps. First step being pre-processing the data. That is, you have to convert your MP3 music samples into the format that could be understood by the computer. As we know, computers don't understand anything other than numbers. So you first have to pre-process your data. And once you have pre-processed, you have to train your model. You have to make it, you have to teach it what the music actually means. So once you have trained the model, you're good to go. You can start generating music out of it. So the third and the most important step is generating music out of the trained model. So let's look into each one of these three steps in detail. So to start with, comes the pre-processing of data, where you convert your MP3 samples into something called as Numpy tensors. Now, how do we convert our MP3 samples into Numpy tensors? There's a series of steps that we follow to do this. So most of you might be knowing MP3 music samples are not the original form of music. They are the compressed version of music. So we human beings, we are OK with listening to music with little bit of frequencies which are missing. But then when we are feeding it to our model, we have to make sure that the music that we feed in is clear, precise. And hence, we first uncompress our MP3 files into something called as monaural wave files. So this process of uncompressing is done using a package called as LSTM. And there is one simple line of code to do that. So you first uncompress your MP3 samples into wave samples, and that wave sample is stored in the form of Numpy array, which is the optimized version of normal arrays. So once you've uncompressed and stored it in the form of Numpy array, this entire Numpy array can't be fed to the model as such. We first break it down into smaller blocks, and to make sure that all the blocks are of equal size, we zero pad the last block. So once we have zero padded it, we still have one tiny little step to follow before feeding it to our model. So whatever the data that is present right now is in the time domain. We first have to convert this into frequency domain because it's easier to work with frequency domain when compared to time domain. So we do it using discrete fast Fourier transformation, and math behind DFT is out of the scope of this talk. But you can see how simple it is to do it with Python. You just have to do numpy.fft.fft and send the block that you want to convert into frequency domain, and you're good to go. So your music sample is now in the format that could be understood by the computer. You first uncompressed it, broken it down into smaller blocks, made sure that every block is of equal size, converted time domain into frequency domain, and now you can feed it to the model. But the big question that arises is, what model do I use? Since then, I'm talking about model, but what exact model was I referring to? Can I write a hard-coded set of formulae to generate music? Can I? Maybe no, because in that case, the model will always be producing similar type of music. But we are more precisely looking for the model that can generate variety of music, which can learn through instances, the model that can make itself better over the period of time, as and when you train it with more and more examples. So the best model that fits in our requirement is artificial neural network. So artificial neural networks are something that are inspired by biological neural network. They resemble our human brains in two main ways. First is they learn through instances, like as and when you feed more and more data, they start getting better with their output. And secondly, whatever knowledge that they have acquired, they store it in the form of synaptic weights. So you can see the nodes over there are equivalent to neurons of a brain, and each node is connected to each other with the help of synaptic weight. So they make themselves better by adjusting the weights between these nodes. So now that we have known, neural networks are the one that does our job of music generation, the next question that arises is, what precise model of neural network are we looking at? So we use a type of neural network called as recurrent neural network, where every node of neural networks takes in both current input as well as the input from my previous node. And that is how it is able to remember information that it had learned in the previous session. Basically, that is how even we human beings learn. Whenever we come across with any new object, we don't start thinking from the scratch. We build upon the knowledge that we already have. So that's basically how even RNN is trying to learn. It takes both current input as well as input from the previous node, does some processing, and gives an output. And this continues. That is how it is able to remember information for a certain period of time. But for music generation, what we are looking for is we want certain important nodes, certain important information to be remembered for a longer period of time. Here you can see at every node, the data is getting overwritten. So the information that is learned by my first node might not be remembered till like 100th or 1000th node. So how do we do it? How do we make our model remember important nodes for a longer period of time? So for that, we use a special type of recurrent neural network called as LSTMs, where LSTM stands for long short-term memory. The best part about LSTM is remembering information for a longer period of time is its default nature, not something it struggles to do. So we saw the recurrent neural network architecture some time back, and we saw at every node the information is getting overwritten. But how exactly does LSTM manage to remember information for a longer period of time without any problem? So to understand it, let's quickly look into its architecture. So Persistence of information for longer period of time is possible because of the horizontal line that you see at the top, which is called a cell state. Now, that is the one which is responsible for carrying information for longer period of time. To give an analogy, you can think of LSTM as a company where if you want to carry forward the legacy of the company, you have to make sure that every employee who is working hard will get promoted, and those who are not working up to their expectations will be sadly terminated. That's basically how even LSTMs try to work. Here, so step 1 in my LSTM is to forget things that are not necessary. So here, this is done by a neural network layer called as forget gate layer, which takes both current input as well as the input from my previous node and gives an output ranging between 0 and 1, where 0 indicates forget everything that you have learned, and 1 indicates retain everything that you have learned till now. So anything between that is the combination of those two. So forget gate layer decides what is to be forgotten. And secondly, input gate layer and tanh layer, these are the ones which decide what values in my cell state has to be updated. So basically, input gate layer decides what values will be updated, and tanh layer gives an actual candidate vector which represents with what values those positions will be updated to. It's like manager deciding which all employees will get promoted, and tanh layer coming and deciding to what extent every employee will get promoted to. So these two were just deciding phase. We just decided what is to be forgotten and what is to be updated. In the next step, we actually update our cell state based on the decision that these two layers have made. So now in the third step, my CT-1, that is previous cell state, gets updated to CT. And final step is to decide what is to be given as output. So this is similar to the traditional recurrent neural network model that we saw in the beginning. It takes both current input as well as the input from the previous node, does some processing, and gives an output which will be fed to the next node of the current layer as well as the next node of the next layer. So these were 4 steps, and this is how LSTM manages to remember important nodes for a longer period of time. So this was all fine, nice to listen to, but what about coding? Are we looking at some 2,000 to 3,000 lines of code? Maybe. Let's see. So how to do it with Python? So Keras offers a library called as LSTM. You just have to import the library, and you have to import a model called as sequential, where every layer of neural network gets added one next to the other in a sequential manner. And you have to instantiate the model. And finally, you just have to add LSTM layer to it. So that's how simple it is in Python. So for LSTM layer, you just have to mention how many input nodes you want, how many hidden nodes you want, and how many output nodes you want. And there you go. Python creates LSTM model for you. So we saw how pre-processing was done. We also saw what model we'll be choosing. The next thing that comes in our music generation is training our model. So whatever the Numpy tensors that we got after pre-processing, that will be fed as input to the input nodes of recurrent neural network. Those input nodes trigger the corresponding hidden nodes, does some processing, and gives me an output. Since during my initial phase, model hasn't learned anything, it doesn't know anything about music, my predicted output will be much different from my expected output. Now this difference is called as error. So the entire goal of training is to minimize this error, to make it as less as possible. So we do it by backpropagating this error. By backpropagating, I mean traversing one layer to the previous layer by adjusting the weights between the nodes in such a way that during my next iteration, the predicted output is much more closer to my expected output. So the way this weights are adjusted depends on the algorithm that you have used. So in our case, we used an optimizer called as RMSprop, and the loss function that we used was mean square error. So the main goal of training was to make sure that this loss function reaches its global minima. So you continue this forward pass and backward pass, which is called as one epoch, until the time the loss function reaches its global minima. Once it reaches its global minima, you can confidently say that your model has now learned what the music is, and it is good to generate its own music now. So before going into generation phase, let's quickly see how we can do it with Python. So as I said, you have to repeat this entire procedure of forward pass and backward pass, that is one epoch, until the maximum number of iteration is reached or the model reaches its global minima. So once it is done, you are good to go. So finally, the generation phase. Now that the model has been trained, what we do is, in order to start the generation phase, we have to give something called as basic seed sequence. So what do I mean by seed is, it's the basic note that we randomly pick up from the training data, we feed it to our model, and model predicts the next node, which is appended to the current node, and is again fed to the model. So let's see how it is done. Say if a is equal to x0, x1 up till xn is my basic seed node, which is something like this. Now this is fed to the model. It predicts the next node. And this node is now appended to the current seed. And is again fed to the model. And it predicts the next node. And this cycle is continued based upon the length of music that the user wants to generate. So this generating the music has two steps. First is randomly picking up the seed. This is totally, you can experiment with this. You can either give your own seed data or you can randomly pick up from the training data. And next is sequence generator, where you send both all model, your seed, and max sequence length, defining how long you want the music to be generated. And the model generates the music for you. So all this is nice to listen to, but we had lots of challenges that we faced. And one main challenge was it was data intensive. So to make sure that your model produces variety of music, it first has to know different kind of music. So you have to sit and collect variety of music. So since MP3 files are easily available, we collected MP3 samples and we scraped data and we trained our model with those. And secondly, it is memory intensive. As I told before, we are working with wave sample when compared to rather than MP3. So 1 MB of my MP3 file will occupy nearly 10 MBs of wave file. So you can see corresponding tensors will also occupy a lot of space. So we are not working with 1 or 2 tensors, but here we are working with hundreds of tensors. So before doing this entire process, make sure that your system has enough memory. And we started off doing this on AWS instance with 32 GB RAM and 8-core CPU. And finally, it's time intensive. This is little annoying because when we started doing it on CPU instanted machine, it took us like 3 days to complete 2,000 iteration. And yeah, so when we switched to GPU, it took like 14 hours to complete 2,000 iterations. So whenever if you want to make any changes, you have to at least wait for 14 hours to see some useful result. So you may think, why do I have to do 2,000 iteration? I can stop it at 100 iteration as well. So in that case, this is what the output will be. You can listen to. So yeah, it's just noise. Your model hasn't learned anything. So you can't stop at 100 iteration. You at least have to do 1,500 or 2,000 iteration to start, for your model to start generating some good music. So this is what we got after 2,000 iterations. So yeah. And here are some of the Python libraries that we use. We use lame and socks to convert MP3 files into different file formats, such as WAV. And we use Numpy and scipy for various mathematical computation of tensors. We use matplotlib for the visualizing input. Whatever graphs that you saw initially was visualized using matplotlib. And we used Keras version 0.1 with Theano as the backend. And the entire code is available on GitHub. Here's the link for it. And even if you didn't understand whatever I spoke for past 20 to 25 minutes, here is the TLDR version of the talk. So you just have to run these 3 commands to generate your own music. So do Python convert directory.py, which does the pre-processing. Do train.py, with where you can play around with number of iteration, epochs, and batch size. So you can experiment with it. And finally, run Python generate.py, and you get your own generated music. So again, in Python generate.py, you can play around with basic seed sequence that you feed into your model. You can give your own seed sequence, or you can randomly pick up from the training data. And you can see what different sort of music will be produced with different seed sequence. And so to tell based small, this entire project was a part of my summer internship project after my sophomore year. So this was carried on in Unnati Data Labs, thanks to my amazing, amazing mentors and team, without whom this wouldn't have been possible. So a big thanks to them, and thank you for attending the talk. But before closing my talk, as I had promised, here's the answer to the question that I had asked initially. So yeah, any guesses? Sample 1 or sample 2? No. This is the generated music, sample 2. Thank you. I hope you enjoyed. It's okay, I'll take it later.
Take questions later?
Yeah.
Okay. All right. Thanks everyone for coming. Padmaja will take questions outside later. So please have an excellent, excellent rest of your day.